So what I am saying in this lecture, we will be talking about the eigenvalues and eigenvectors. The eigenvalues, as I said, they are a larger set where the subset of that one is the pole of the system. For example, if I have, this is the state space representation, and this is the transfer function. There is a possibility is that my transfer function or the stability from the input output point of view, the system is stable, but if I take the stability of the state space, the system is unstable. There is one possibility. That's why the eigenvalue will give you more information about the system. What will happen at a certain time, there will be a pole zero cancellation. That's in certain system, it will lead to, let's say, S minus 1 over S minus 1, S plus 1. So the transfer function here is equal to 1 over S plus 1. So the transfer function is stable, while I will have two eigenvalues. One of them is unstable. So basically, the eigenvalues, we could use them in study the stability of the system. This is one application. What about eigenvector? The eigenvalue and eigenvector, we could also use them. Suppose you have a general A matrix, general matrix A, and I would like to diagonalize it. I would like to have a diagonal. I can do that where the elements, if my eigenvalues are distinct, I will have the new matrix. I can move this matrix into a diagonal matrix by applying certain transformation that basically I will pre-multiply the matrix A by the eigenvector matrix and post-multiplied by the inverse of the eigenvector, or the other way around. So I can, one of the applications is diagonalization, is making the, looking into this thing from different perspective, where the diagonal matrix is extremely simple to understand. Okay, so those are two, at least, there are two applications in control system, and Abraham mentioned in physics, you can think about the motion, and definitely there are many applications for it. Okay, now, how do I find the eigenvalues? Well, the eigenvalues or the eigenvector, look, the eigenvector is defined, okay, if I have a matrix A, there will be an eigenvalue associated with A, and for each eigenvalue, there will be a certain eigenvector, such that AX equal to lambda X, okay? We are looking into this equation where X should be different from 0. I would like, because otherwise, if X equal to 0, it will be trivial solution, and it's useless for me. It's useless for everybody. Okay, you can think about the eigenvector. I'm scaling the vector by a matrix A, which is the same as scaling the vector by a scalar. Okay, now how do we find the eigenvalues? If you are given a matrix, how do you find the eigenvalues of the matrix?
Take the determinant of A minus lambda I and equate it to 0.
Okay, so wait, what you are saying, the determinant, okay, why is that? Because look, if I have AX minus lambda X, so I'm putting it in this format, and let me factor the X out. Suppose A minus lambda I is invertible, that basically I have A minus lambda I, an inverse multiplied by A minus lambda I X equal to A minus lambda I inverse times 0. If this is invertible, what do I get in here? From those two, what do you get?
X equals 0.
identity times x equal to 0, which is basically x equal to 0. So what I need in order for me to find non-zero eigenvector, this matrix should not be invertible. Okay, this matrix should not be invertible, or the matrix should be, okay,
Determinant should be 0.
Singular. Okay, the matrix should be singular. Remember, okay, A minus lambda I inverse equal to the determinant times the adjoint of the A minus lambda I. So if I'll make the determinant equal to 0, then the matrix become singular, and that will give me the eigenvalues. So the to find the eigenvalues, lambda I, you set either lambda I minus A or A minus lambda I. This determinant equal to 0 and solve. That will give you how to find the eigenvalues. Once you find the eigenvalues, you can go back to this equation, and for each eigenvalue, you are going to get an associated. Solve this equation, you can get the eigenvectors. Okay, so basically, this way we will be getting our eigenvalues, and the polynomial which we are getting from this by setting the determinant equal to 0, called the characteristic equation. And if we are talking about transfer function, most of the time the transfer function, the denominator of transfer function, it will be the characteristic equation. Any question here? Any question here, Shabab? Okay, let's take an example. Ahmed.
Yes.
How do I, okay, I would like to obtain the eigenvalue for this matrix. Can you tell me, how do I apply my formula? We said we need lambda I minus A, or A minus lambda I. So what is the identity now? What is the size of the identity matrix now?
2 by 2.
Any guess, Ahmed?
2 by 2.
2 by 2. Thank you. So basically, we will have, okay, lambda 0, 0, sorry, 1, 0, 1 minus A, which is minus 4, minus 6, 3, and 5. And this will give me, this is equal to lambda, okay, plus 4 and 6. In here, I will have minus 3 and lambda minus 5. This is the lambda, lambda I minus A. Take the determinants. So what is the determinant equal to? Any volunteer?
Isn't it A minus lambda I?
It's going to be lambda plus 4, lambda minus 5, plus
18.
18, which is equal to lambda squared. Now I have, so it's going to be what? Plus 4.
Minus lambda.
Minus lambda.
Minus lambda.
Minus 20.
Minus 20.
Minus 20. And
Or minus 2.
Minus, so it's going to be minus 2. Or if I want to get the roots, so it's going to be lambda plus 1, lambda minus 2. So the roots or the eigenvalues lambda equal to -1 and 2. Okay. As I said, you can go and for each lambda, you can find the eigenvector, but we are not going to go to that. I don't think we need it in here. Any question before we move?
Yes, doctor.
Further.
Didn't we say it's A minus lambda I, or?
It is the same because look, I said A minus lambda I equal to 0. Okay. Multiplied by -1. So it's going to be lambda I minus A equal to 0, isn't it?
Yeah. But is there a reason why you multiplied by -1, or you just did that?
No, it's convenience. You can either lambda I minus A or A minus lambda I. It doesn't make any difference. It's a matter of convenience, and both ways will lead to the same answer. Because as I said, this equation, you multiply the equation by -1. You don't change anything. You don't change any values.
صحيح.
Okay. Any other question? Now, let's move into another topic. Okay. I would like to bring the roadmap again. So far, we just finished the modeling part in the course. Where in the modeling, we model, simple system, circuit, mechanical system like spring, electromechanical system, motor generator, DC motor, DC generator. We get the transfer function model. Okay. We get the differential equation model, transfer function, and state space. And we relate them. Okay. So we are done with the modeling. Now we would like to go to the analysis, where we will be starting with, in the analysis, we'll do two types of analysis: quantitative and qualitative. We will do analysis in time domain, where quantitative, that you have a step. Okay, you have transfer function, and your input step, you are going to get an output in the time domain, and you'd like to see how does the system behave. You'd like to analyze. We will be talking about the second order system in particular. Then later on, we'll be talking about stability, where it's going to be quantitative. You are talking about in general, if the system is stable or unstable, not for specific input. Okay? So in this lecture, we will be, taking the second order system. Well, maybe we need this lecture and next lecture to talk about the second order system. Then we will go to the stability. And so far, we have about 16 lectures, I think, so far. We will have maybe 20 lectures for the analysis. And the last thing we will do is the design. Okay, so this is basically what we are going to do. Okay. Well, in here we said we will do the time domain analysis and the frequency domain. Why time analysis is important? Why the analysis in time domain is important?
To see the transient response.
What?
To see the transient response.
Okay, good. But why? Because look, in the time domain, when you're talking about time domain, you see in front of you, you can visualize, okay, how does the output look like? It is time, it's real time. While if you are talking about transfer function, I mean, you have to connect. You don't see it directly in front of your eyes. You have to invert it. You have to think about it. How does it look like? So both of them are important, okay? It is, you know, very powerful quantitative method of stability. We cannot always, you know, get the, you know, I mean, the time domain. It's much easier to go to the frequency domain, and they are related, of course. But it is, you know, sometimes it's important to go directly to the time domain. Okay. Now, well, we will be talking about transient and steady state response. What is a steady state response? What is a steady state response? Abdullah Al-Harithi. Abdullah? Do we have Abdullah Al-Harithi in class?
في ماجد الحارثي.
كيف؟
ماجد الحارثي.
طيب يا ماجد. Go ahead. What is okay? What is الحمد لله في حارثي. المهم في حارثي.
في الحارث بعد يا دكتور.
طيب what is steady state؟
steady state اللي هو نقسم الديفرنشال equation على حسب كم to the order. إذا second order we have two steady state response.
No, not quite. Okay, you solve the okay. You have differential equation. Yes, definitely you need differential equation, but you solve the differential equation. Okay, what is the steady state response? What is the solution? Okay, that's what I'm
when t goes.
Okay.
When t goes to infinity, what is it?
When time go to infinity.
Yes.
Okay, and the system is stable, you reach certain level.
Whether you will have a critically damped or over damped or under damped.
No. For that, okay, we'll come to this one. But let's focus now on the steady state. Steady state is the response where time goes to infinity. And
or S goes to zero.
No, it goes to zero. Then I mean.
Or S.
Oh, S will go to zero. But let's
final value theorem. Yes.
Yes, Abdurrahman. This you can relate it. But what I'm trying to say in here, you should understand in time domain, steady state, it means that you let the time go to infinity. If your system is stable, you reach certain level. If the system is unstable, then your response will be unbounded. And there is no steady state. You don't reach steady state. So steady state is associated with stability. What about transient then? What about transient?
Transient, يعني you have an input basically. You have, I mean, not input. I mean, when you take the differential to or the solution to infinity, you will have a source
response. This is steady state. We said this is steady state. What's transient?
Transient معناها dependent on time. يعني it's not.
معناها
it vanish with time.
Exactly. It is basically the period before I reach the steady state. Maybe my system, there is a possibility, let's say, a typical response like this. So, suppose I have a step input. The input, my output, y of t, will overshoot and will oscillate, then it will go to certain value, steady state. So I can consider this is my, transient. Okay, this is transient. And this is steady state. So the transient is before you reach the stability. Okay, in the time domain, we are going to talk about overshoot, settling time, time to peak, time to rise. There are certain specifications. So basically in here, what I'm saying, this is the overshoot. This is the amount of the overshoot. You know, suppose I have an input of step input. One, my input is step. I have a system. This is, let's say, U of t or R of t, and this is Y of t. My input is step. There is a possibility my system will oscillate like this. It will go little bit beyond the one. That's where it says the percentage overshoot. And then it will go down. The settling time is how long it will take me to go and reach the steady state. The peak time is the time where, you know, what is this time? T, I call T peak. We'll come to it. We'll come to them. But those are specification, okay, we will be using, okay, we will be using in, you know, addressing the second order system. The steady state error is very important. Okay, what we are going to do, we will be studying, you know, the input for the system, special input, step, ramp, and parabolic possibly. If I understand the behavior of the system for these type of inputs, then I can, you know, understand the behavior of the system for any other inputs. There is a correlation between, okay, the performance and the location of the poles and the zeros of the system. Okay. The development relationship between those performance specification, we are going to, for the second order system, we are going to have two quantities called natural frequency and the damping factor. Those will, you know, will be characterizing the second order system. We will be talking about also the dominant poles. Okay. We are saying in here, why second order? Why do we study second order system only? Why we focus on second order system?
Can be extrapolated.
Okay.
It can be extrapolated.
Well, yes, second order system is easy to analyze. And it could represent good number of, you know, system, and it could also approximate, that's the notion of the dominant pole, approximate higher order system. For example, suppose I have a transfer function. In transfer function, I have the following. I have 3 poles. Okay, this suppose G of S equal to this one. Okay, if I want the impulse response, how do I get the impulse response? I will write this as A over S plus 1 plus B over S plus 2 plus C over S plus 100. That's basically, I will do the partial fraction. Now tell me what G of T will look like. What G of T, you know,
e to the power minus
A, B, C. So it's going to be A times what?
e to the power minus t.
Okay, plus B minus
e minus 2t.
plus C e to minus 100 T. Now, let me see. We need just 1 second. Firas, we have 2 Firas. Firas Al-Hussein. Firas Hussein or the other Firas. What about
Yes, Doctor.
تفضل. Go ahead. Now, tell me which فراس we are talking about الحين. أي فراس؟
Yes. دكتور فراس حسين.
ما نسمع صوتك، صار في إيكو بالسماعة حقتك. Firas, my question is, at t equal 1 second, what will be the value of this term?
Can you hear me, Doctor?
والله يعني بس المشكلة. Okay, tell me quickly what is first of all أي فراس أنت بيهم؟ Well, how about you, Hadi?
Yes, Doctor.
Okay, after 1 second, what will happen to this term? What's the value of this term?
E to the power minus 100.
To minus 100.
Yes.
After 1 second.
Yes.
Kam?
E to the power 1 minus 100.
Yes. Tell me, roughly speaking.
Just we substitute 1, right?
Yeah, substitute 1. Tell me. Look,
E to the power minus 100.
طيب قول لي كم يطلع؟ عندك كالكوليتر حقك بجنبك؟
زيرو يا دكتور.
You don't need the calculator شباب يعني.
زيرو.
Very small number.
Exactly. That's what I want to say. So I can neglect this part and approximate the g. So g of s approximately equal to 1 over s plus 1, s plus 2. And the performance will not be affected by ignoring the pole which is far away from the others. This is called the dominant poles. The dominant minus 1 and minus 2 are dominant, while s to the minus 100 is, you know, in the s plane. If the pole is far away in here, okay, and the other near the j omega axis, those will be dominant while the other has no effect. That's basically what we mean by dominant poles. We will come and, you know, give the criteria when we will, you know, do this approximation. This is roughly speaking. Of course, I mean, suppose C, it happened, C will be 10,000. Is your approximation accurate?
Yes.
No. If it's 10,000, no. You are.
لأنه e to the power minus 100 يا دكتور ترى 10 to the power minus 44.
طيب اوكي خلينا نقربها شويه خليها
حطها 10 to the power 44 تصير not accurate.
طيب اوكي اقول لك خلي system in which okay this will be billion.
Even billion.
No. Look. This is, I mean, we are doing this one, but what I'm saying, if you want to go for more accurate,
لأنه E أصلاً is vanishing.
there are other methods of doing it. Okay, but roughly speaking here, I just want to give the idea. The idea is that, you know, there is the concept of dominant pole. It means that, you know, some of the poles are far away, so I will neglect the effect of them without affecting the behavior of the overall system. Okay. Well, the transient again, coming the transient response is the response that disappears with time. Steady state, a response that exists for a long time. Provided that, as I said, provided that the system is stable. If the system is unstable, then it's useless. Okay, there, I mean, definition is not correct. The system performance will be characterized by both transient and steady state. So we will be, you know, given specification, how can I have, you know, good response for the system? So for good response, I mean fast transient and steady state without much of errors in there. Okay. A fast transient may involve significant overshoots, which is not desirable. So this is basically, as I said, this is the typical response of second order system. I have my input is step of 1. Then when you switch on your system, the system will overshoot first and then oscillate, and ultimately it will go to steady state. Now, from real life, what's overshoot? What's an example of overshoot?
DC motor.
DC motor, okay. Where is the overshoot will come?
At first, it will not oscillate to the maximum speed, then it will reach stability after some time.
Exactly. Great. Okay. Other application for it, suppose you are filling certain tank with liquid, and you realize that the tank is going to be filled. You try to turn off the valve. Between turning on the valve and the time the liquid reach your container, it might be, you'll go over the desired one. Then, of course, if you are using a tap, you can, discharge and ultimately you will reach. So the overshoot, it is basically you will go over your desired value. And what we are going to talk about, the percentage overshoot, how much I can tolerate in overshoot. Can I get the overshoot infinite overshoot? Definitely there is certain limitation. After a certain time, you might end up by, unstable system if you don't control the overshoots. Then we'd like to see when do I reach this overshoot, okay? One of the specification is the rise time. The rise time is the time to go between 0.1 and 0.9 of the response. The shortest the time, the speed will be more, the speed will be higher. Speed of the response will be higher if we shorten the time rise. The settling time, okay, when I will be reaching the steady state. And the steady state error. Okay, how much I can tolerate in steady state error, and how can I eliminate this steady state error if there will be a steady state error? We will be talking about all of those specifications in this lecture and the following lecture. Sometimes, in here what we have, you would like to have, okay, sometimes you have, two performances for one parameter. And they might conflict. You satisfy one, it will conflict with the other. So what you try to do, reach a compromise where you will be doing good in both of them. For example, in here, we will see that if I need my system to be, fast, okay, there is a parameter will come, the damping factor should be, small. But small, it means that more overshoot. So you have to, as I said, you have to compromise sometimes in the specification. Well, the type of input, as I said, which we are going to test, the step input, ramp, and parabolic. The step, basically A, where the step size is A. It is equal to A if t greater than or equal to 0. And the transform, in the transform domain is going to be A over S. The ramp is going to be AT, and in the S domain is going to be A over S squared. We will be studying all of those type of inputs. Well, if you want the MATLAB command, okay, MATLAB can, I can get the response by using MATLAB, and where this is very useful, this is one of the command, LISM, okay. Okay, this will, this is a good command to, give you the response of the system. There is other command, if you have step, there is a command called step, and it will give you the step response and so on. So this is basically, it will be, in MATLAB, and sometimes you'd like to get information from the MATLAB. Well, we will be talking about the impulse response. If I have a system, okay, how do I get the impulse response? What do I do? How do you get the impulse response of a system?
Input a delta function.
Yeah, your input should be delta function. So the impulse response be the inverse of the transfer function. or the step response. Okay, the step response, either you convolve the step with the impulse response, or take the Laplace transform. For example, I have a system G equal 9 over S plus 10 and U equal 1 over S. If I want to get the Y of S, what's Y of S equal to? What's Y of S equal to?
Multiply it.
Okay, 9 over S plus 1 times 1 over S, which is equal to, if I want to do a partial fraction, let's say this is S, this is S plus 1. What do I have in here?
+1, a constant.
0.9.
9.9. 9 over
times it.
Okay, how about the other one? The other one, if you eliminate eliminate this one, so it's going to be minus 9.
بس في المقام.
Okay, so if I want to go to the time domain, y of t then equal to what?
There is a 10 دكتور in the denominator.
0.9 minus 0.9 e to power minus t. What will be the steady state? What will be y at steady state?
Take infinity.
Equal to 0.9, isn't it?
Yes.
So basically, look, what we have in here, there is an error because my desired input is a step. What I'm getting is 0.9. This means that I'm going to have a steady state error. Okay, so we will be studying, okay, how do I eliminate this error? Usually, look, if you set G of S, G of 0, sorry, equal to 1, you don't have any error in the system. If G of 0 different from the, this is by using the final value theorem, okay? But anyway, what we are going to do, we are going to, do the analysis or the steady state error. We will be studying the effect of the step input and how do I eliminate, if there will be steady state error, how do I eliminate this one? How can I design a controller which will, eliminate this error? Or if I have ramp input, then the error is going to be possibly, for this type of system, possibly the error is going to be infinity. Okay, so we will be, as I said, we will be, inshallah, maybe in the next lecture, we will